Hello everyone, this is part 5 of module 5 data communication. So module 5, so far we were discussing the different synchronization mechanisms. We started our discussion with what is synchronization problem that can occur in a typical communication. We taken an example and we observed the issue. That is, if the receiver clock is having some drift with respect to the sender clock, what is going to happen? And then we saw the solutions like two modes of communication: the asynchronous transmission and synchronous transmission. And we saw in detail how these transmission techniques are working and their pros and cons, everything. So hope you got a clear concept of synchronization issue and its solutions. Okay, and at the end I think you were able to differentiate between the synchronous and asynchronous transmission technique. Now we move on to our discussion on error control mechanisms. Okay, so we are simply focusing our attention from now onwards on different error control schemes like error detection and correction schemes. And what is error? We start our discussion with the definition of different types of error. Okay, so let's begin with types of error. So before that, what is error? So in digital transmission system, an error occurs when a bit is altered between transmission and reception. So when the sender sends some information in the form of binary, that is zeros and ones, through a transmission media, it will be received at the receiver side. Now on the way, if a bit is due to this transmission impairments and all, there are chances of signal voltage level may change, right? So accordingly the information being decoded at the receiver side may be different from what is being sent at the sender. So a bit is altered in the sense currently the sender may be sending that bit as 1 and the receiver may be interpreting it as 0, or 0 is being sent and it is interpreted as 1. So both situation can be in general termed as error in our digital communications. That is, a binary 1 is transmitted and a binary 0 is received, or a binary 0 is transmitted and a binary 1 is received. So this is the simple definition of error in digital communication. Now basically we have two types of errors, that is single bit error and burst error. So what is single bit error? The word itself says that a particular bit of our communication is altered and rest of the bits are received correctly. Okay, single bit error is an isolated error condition that alters only a single bit, only one bit, but does not affect the nearby bits. So definitely we have the burst error where instead of a single bit, a number of bits, nearby bits are getting altered. So a burst error of length b, but you have to be very careful about the definition, how they are defining burst error of length b is a contiguous sequence of b bits in error. Okay, so b bits are in error. We can say that there is a burst error of length b. But there is a condition that out of these b bits are in error, means we don't want all the b bits to be error. When you observe some b bits, you saw a kind of cluster of bits which are in error. That means out of this b bits, some of the bits may not be in error also, but still you can see some kind of cluster of error in that area. Okay, so to make it a burst of length b, the condition is that the first and the last bit out of the b bits, the first and the last bits should be in error, and any number of intermediate bits are received in error. Okay, so we just have the condition that out of the b bits, the first bit and last bit should be in error. That means the first bit actually being sent by the sender as 1 and is first and last being received by the receiver as 0, or 0 is being sent and 1. That error condition should happen for the first and the last bit. And between the first and last error bit, that means you can see a kind of single bit error for the first and last bit of the burst b, and between these erroneous first and last bit, the intermediate bits, we don't want all the bits to be erroneous. Some of them are erroneous, and in worst case maybe all the bits are all showing error also. But at the same time there are possibility that some of the intermediate bits between the last and the first erroneous bit may be received correctly also. So that is allowed. Okay, so that difference you have to be clear about it. So accordingly, we have a standard definition for burst error as per IEEE standard 100. In that documentation, we have a standard definition for burst error, and also by ITUT recommendation. Both of them define this error burst as. So ITUT and IEEE, two standards that we are using in our communication. And according to both standard, the burst error is defined like this. This is a formal definition. A group of bits in which two successive erroneous bits are always separated by less than a given number of x of correct bits. So two successive erroneous bits. Okay, definitely the last and the first bit as per the previous definition. I would suppose the error burst is of length b, the last and the first bit, that is what they define by a group of bits in which two successive erroneous bits. Between these erroneous bits, they are separated by. So we know that. So here they are trying to define a length for b. Okay. So the out of b, the first and last bit are erroneous, and in between, any number of intermediate bits are received in error also. Now between two erroneous bit, how many intermediate bits you can allow? So that is what the standard is trying to say. So between the successive erroneous bits, they are always separated by less than a given number x of the correct bits. So this should be defined. Okay, so when you have a communication system, you can define what is burst error according to you. Accordingly, you can set your algorithms they are handling in the sense detecting as well as correcting the burst error. And this is a kind of parameter. It is not a constant fixed value as per the standard. They are just making it as a variable. But such a variable should be defined in any algorithm which are dealing with the burst error. Okay, so that is up to the communication engineer. When we are defining a particular communication system, you can make this x as a parameter. So the last erroneous bit in the okay, so that is the thing between two erroneous bit which makes a boundary of your burst bit. There should be separated by some x number of bits. Okay, so that x can be of any value that is defined by the communication system. Now out of these x bits, we don't want all the x bits to be in error. Okay, so that is another thing. There may be some of the bits out of this x are in error, or in worst case all the x bits are in error also. Both are fine. That means you are allowing some correct bit also within a burst error. Okay. Now put in another way, the last erroneous bit in the burst and the first erroneous bit in the following bursts. That means if you are looking at a sequence of bits, you can see different burst error, like some cluster of erroneous bit at different point. Okay, so look at the current burst, what is the last erroneous bit, and look at the burst which is following the current burst, what is the first bit. Okay, so between these two, I mean the last bit of the current erroneous burst and the first bit of the following burst error, between them the number of bits should be x or more. Okay, because if it is less than x, that will make another burst between them. So we have a current burst, that is a kind of cluster of erroneous bits, and we have another cluster of erroneous bits making the next subsequent burst. Between these two bursts, the number of bits has to be greater than x. If it is less than x, again we will be having an intermediate burst also. So that can also happen. Okay. So if otherwise it should be greater than x bits. So hope the definition is clear for you. So some observations. Thus, in an error burst, there is a cluster of bits in which a number of error occur. Although not necessarily all of the bits in the cluster suffer an error. We don't want any requirement that all the bits in our cluster making the burst error are to be erroneous. We need the first and last bit to be error, so that make the boundary of your error burst, and between the first and last bit some less than x number of bits can be erroneous, at most x number of bits. So burst errors are more common and more difficult to deal with. Definitely bit error means compared to single bit error. Okay, so that is obvious, right? So the effects of burst errors are greater definitely at higher data rate. So when the data rate is increasing, the number of bits which are getting which are suffering this burst error will increase. So how it is going to be affected, we will see in an example here. So burst error example, burst errors can be caused by any kind of transmission impairments, particularly at this impulse noise. We already seen what is impulse noise, sudden impulse or spike that is happening in our communication, some kind of external disturbance. Okay, so for more detail you can see the session where we discussed different types of noise. Or another cause is fading that is happening in a wireless environment. Fading, as a name suggests, is kind of attenuation only. Normally we use the term attenuation with respect to wired communication. So when it comes to wireless communication, normally the terminology used is fading. So that can cause due to different situations, like the environmental conditions, the geographical region where you are using your communication system. Depending on all these features, this fading can occur with a different intensity. So because of this kind of not only this is some dominant reasons. Other than that, all other types of noises, means attenuation, delay, distortions, everything can lead to not delay, distortion, attenuation and other transition impairments can lead to burst error. Now, if I have, for example, an impulse noise event or a fading event in a wireless communication of 1 microsecond occurs. That means for that 1 microsecond of time, your transition media is under this particular disturbance, whether it is impulse noise or fading. 1 microsecond of time, the transmission media is having an effect of it. So definitely all the bits which are communicated during this 1 microsecond of time are vulnerable to be in error state, but sometimes they may escape also. So chances are high. Okay, now if you are having a transition media which is working or providing you 10 megabits per second data rate, then there is a burst error of 10 bits. Why it is so? Because 1 microsecond of time the channel is under external disturbances, so chances of error is high during this 1 microsecond of time. So in every second 10 megabits are getting communicated. So how many bits can be communicated during 1 microsecond of time? So 1 second 10 megabits, that is 10 into 10 power 6 bits per second. So that is in 1 second. Then in 1 microsecond, that is in 10 raised to minus 6 a second, how many bits will be there? 10 megabits. You have to multiply it with 10 raised to minus 6, right? So already mega is 10 raised to 6. This micro 10 raised to minus 6 both get cancelled and you are getting 10 bits as the answer. So in every second, the transition media is trying to transfer 10 megabits. Then in 1 microsecond, how many bits are getting transmitted is 1 microsecond into 10 megabits. That is 10 bits. Okay. Suddenly, if I have an increased data transmission rate, say 100 megabits per second, then how many bits are in error condition? In every second, 100 megabits are communicated, 100 into 10 power 6. So in 1 microsecond, it is 100 into 10 power 6 into 1 micro. That is 10 raised to minus 6. 10 raised to 6 and minus 6 get cancelled, 100 bits. So you can see that as the data transition rate is increasing, the number of bits which are getting this burst error is also increasing. So that is a statement we made in the last slide. So hope this is clear. Now, means if you are looking at the discussion of this error control schemes in that William Stallings textbook particularly, they are defining certain probability values, and with respect to that they are trying to model most of the techniques we have. So no need to know that much mathematical background, but still it will be better if you have a flavor of it, because if you are reading it, if you are doing some intensive reading on this topic, this will help you. Okay, so just understand what are the probability values that are normally defined with respect to errors in a transmitted frame. So we have some 4 types of probabilities mainly. The first one, PB, that is defined to be the probability. This notation is something that textbook oriented, but if you are looking at different textbook, they may also use these probability values for at different situations, but they may be using some different notation. So this is notation used in Stalin's textbook. Just understand about the concept. Okay, notation you can use anything. So PB is here taken to be the probability that a bit is received in error. That is the bit error rate. Okay, so whenever you are sending a particular bit, it may be received in a different voltage level. So that is what we defined as an error, right? So what is the probability of occurring such an error? So to what probability a particular bit being sent by the sender is received by the receiver, but it is something different from what is sent by the sender. It is erroneously received by the receiver for a particular bit. So that is the rate at which a bit level error can occur. Okay, so we call it as the bit error rate, BER. Now another terminology is P1, that is a probability that a frame arrives with no bit errors. Okay, so what is a frame? That is if you look at our asynchronous communication, that a frame is just a character length, maybe 10 bits, around some 8 bits of information, maybe with a parity, with a start and end synchronization bit is what makes a frame. But in general, as I already told you, we are using synchronous communication in most of the current scenario, where if you are looking at some Ethernet and all, frame is actually something bigger than just a character. Normally some a block of bits you can define like that, maybe some 1024 bits or more than that, 1 megabits, like that. Whatever that depends on the type of LAN protocol which you are using. Okay, based on its performance, efficiency, etc., we will define a boundary for the frame. So frame is simply a sequence of bits, that's all. And out of the sequence of bits, we have some special preamble, postamble for the synchronization purpose, along with some kind of control information, everything. Okay, so they all together make the overhead of the frame. Everything we've already seen. So if you simply look at a frame, that will be a collection of bits. Okay, and now the receiver is receiving a frame as a whole without any error. That means none of the bits in the frame is erroneous. Okay, to what probability we can expect that to happen in the receiver? Okay, so that is P1. How these probability values are measured? That is from definitely some expected value from our past experience. We will be measuring this. Okay, so previously, say in last 1 hour, this many frames were received, and out of them these are received without any error. Okay, maybe you can take any time frame, like last 1 hour or last 2 hour, whatever it is, and with that time frame you will be defining your error probability, like this many. So how many are in error divided by what is the total. Okay, so that is how you are defining it. You will be getting a value between 0 and 1, because it's probability value, right? Now P2 is another probability that is being defined, that is probability that with an error detecting algorithm in use, you have an algorithm which is running at the receiver side that can detect whether there is an error in a frame or not. Okay, normally we will be running this error detection algorithm or correction algorithm, whatever it is, for the whole frame, not in a bit by bit manner, because it is definitely time consuming and tedious. So for a frame as a whole, we will be running our error detection algorithm. And we have a very good error detection algorithm being used at the receiver. But even we don't have any error detection algorithm which can trace error 100% of the time. Okay, so most of the this error detection algorithm that we will see, we can see that 100% in certain situation they are means more practical error detection algorithms are not 100%, but some are proposed in theory, but when it comes to practical application they have some other kind of complexity and difficulty. Okay, so anyway, we will see this error detection scheme. That time I will explain. The most popular error detection scheme is the cyclic redundancy check, CRC code, but many are there in literature, but the CRC is something popular due to its simplicity in implementation and all, and many other parameters. So that is the one which you are going to study in this session, in this 5th module. It is there. Okay, and if you are looking at CRC, it is not working in all the cases, but majority of the cases are being solved by CRC, and special CRC polynomials are there by which we can trace some maximum amount of errors, but still don't expect 100% error detection. So in that case, suppose you are using a very powerful error detecting algorithm, then still a frame may arrive with a probability that some of the frames are having undetected error. A frame may arrive with some undetected error. At the same time, the frame may arrive with detected errors also. So both probability you have to define. So P2 is defined to be the probability that using a error detection algorithm, a frame arrives with one or more undetected errors. Okay, that means this is something just if what is P1, a frame arrives with no bit error. Now P2 is a frame arrives with one or more undetected errors. Okay, even though you are having a good detection algorithm. Now P3 is something that define the usability of a particular error detection algorithm, because P3 is defined to be the probability of an error detection with an error detection algorithm in use. A frame arrives with one or more error if present, that is detected. Okay, one or more detected bit errors but no undetected bit errors. So what is the probability in which you can expect a frame to reach without any error, or even though there is error that is being detected by the detection algorithm? Both are fine, but see, both are positive situation. So that probability is P3. So P3 is high for a particular error detection algorithm, means it is something preferred. Okay, so always you can make this, you can calculate the P3 value for a particular detection algorithm, and you can see what is its performance. Okay, and or you can compare two different detection algorithm with respect to this P3. So that is how P3 is getting value, and P2 is another one, just opposite to P1. P1 means a frame, what is the probability in which a frame is arriving with no bit error. P2 means a frame is arriving with some errors, but some undetected error by using some detection algorithm. So like that, these four probabilities are mostly used for analyzing the performance and all. And assuming this PB, that is the bit error rate, the probability that a particular bit is in error. Okay, let it be a constant value, and it is independent of the other bit, I mean independent for each bit. So a particular bit, what is the probability that this particular bit, the current bit, is in error, is independent of its previous as well as the next bit. That kind of probability you have to take. Let it be a constant value and is independent with respect to other bits. Then we can define something like a P1 is what? 1 minus PB raised to F. So that is something straightforward definition. So what will be F then? The number of bits in a particular frame. So F is a number of bits per frame. So suppose I have a frame with 100 bits. Okay. Now what is the probability that you are getting? What is your P1? You are getting your frame with no bit is in error. That means bit 1 should not be in error, bit 2 should not be in error, etc. The last 100th bit is also not in error if F is equal to 100. Okay, so F is in general the number of bits per frame. Let me take it as 100. Okay, now what is the probability that the first bit is not in error? 1 minus PB for the first bit. That means what is the probability that the first bit is in error? That is PB. 1 minus PB will give you what is the probability that that bit is not in error. I am saying that 0.6 is the probability that a particular bit is in error. Then 1 minus 0.6 will be the probability that the bit is not in error, 45% and 60%. Okay, so it is clear. And we assume that this PB is constant and independent for each and every bit. No. Okay, so in normal cases it will be like that, but there may be some different situations also. In that case, this same thing will happen for the second bit also. What is the probability that second bit is not in error? That is 1 minus PB again. For third bit, again 1 minus PB, etc. For the last bit, 1 minus PB. And you know, in multiplication theorem for probability, you get the final probability by multiplying all, because events are independent, right? Simply multiply them together. So for the frame with the F number of bits, 1 minus PB into 1 minus PB into etc. into 1 minus PB F times, the probability that the frame is arriving without any bit error, means all the bits are error free, is 1 minus PB the whole raised to F. Multiply F times. Okay, if that is the case, then what will be our P2? P2 is just opposite to P1, right? Or P1 means a particular frame as a whole is receiving without any bit error. P2 is you are getting an error with some error, and they are just undetected also. That is some inefficiency of the detection algorithm which you are using. So it will be 1 minus P1. So That's all. Now again, they may ask you some problems also from this formulation, so be careful in that. I didn't see such questions in the previous year. Okay, so the probability that a frame arrives with no bit error decreases when the probability of a single bit error increases, definitely, right? So when this single bit error, that is PB, is increasing, 1 minus PB will be decreasing, or P1 is decreasing. So what is P1? The probability that a frame arrives with no bit error, that is P1, that is decreasing when this PB is increasing. Also, the probability with that a frame arrives with no bit error decreases with increase in frame length, right? This F is also going to affect. Okay, so when F is increased, this P1 is decreased. Okay, and when PB is increased, this P1 is also increased. Just a normal mathematical relation. When PB or F is increasing, P1 is decreasing. Now, what is the meaning of this? How you can interpret it in a different way? Like when F is increasing, P1 is decreasing, means frame length is increasing, more number of bits are there in the frame. So definitely the possibility for a particular bit is in error is also high. So that makes your P1, P1 is something positive. The frame is arriving without any bit error. That will decrease because the probability of error is increasing, right? Because the frame length is increasing. That's all. So the longer the frame, the more bits it has, and the higher the probability that one of these bits is in error. Okay, that's all. With this, we will end up our introduction to error control. So basically, error control means error detection and correction, and those schemes we are going to see in our subsequent parts. So right now we saw just the concept of error and types of error, and particularly you should give attention on burst error, how it is being defined. Okay, that's all. Then we saw some of the some example for the burst error, followed by the last probability values. Okay, hope it is clear. Thank you.